In this video, we'll demonstrate qualitatively the force a parallel plate capacitor exerts on a dielectric. Then you'll see a quantitative demonstration of the force a parallel plate capacitor exerts on a conductor. Finally, when the applied voltage exceeds a critical value, you will see dielectric breakdown occur inside the capacitor plates.
This parallel plate capacitor and an acrylic sheet will be used to demonstrate the force on a dielectric between the plates of a capacitor. The sheet is attached to the end of a balance arm so that it is free to swing up and down. We'll place it between the plates of the capacitor and charge the capacitor to a high voltage using this electrostatic generator. When the capacitor is charged, the force on the dielectric pulls it down between the plates. This animation shows how the polarized molecules of the dielectric are reoriented by the electric field of the plates. This new orientation results in an attractive force on the dielectric, which pulls it down between the plates.
In this part of the video, we're going to show the effect of a capacitor as it attracts a conductor. Here are the two capacitor plates, here and here. Each one is connected to the opposite side of a high voltage power supply that will supply 3 kilovolts. Down here is the piece of aluminum, which is in between the capacitor plates, partially outside, partially inside. All of that sits on top of a balance, which will come up and register 0. It's set in what's called a tare mode, so it'll register 0. And then I will start applying a voltage to this, and you will notice that the reading on the scale will change, and notice also that there is a negative sign that will be over on this side, indicating that the metal is being pulled upward into the capacitor. So I'm going to begin turning on the voltage now, and it'll take a little bit before this starts to show up. Now you will notice that we have reached such a high voltage that we've reached what we call dielectric breakdown, and now there are sparks beginning to go into the region between the capacitor and the conductor. The graph shows the force versus the voltage squared. The constant K depends on the material and the geometry, and the epsilon naught is the usual value that you've seen in your class. What's to notice is that these forces are extremely small, never exceeding much more than about 25 millinewtons for the full 3,000 volts applied across the capacitor.